Hello and welcome to the third workshop of the Canadian Geography Workshop series. In this workshop, we're going to talk about liquid water on Earth. So we're going to talk about water on land, so rivers, lakes, wetlands, and so on. We're going to talk about our oceans, so the topic of oceanography. And we're going to spend a bit of time discussing groundwater. In this workshop, it's going to be about liquid water. So we're going to discuss water in the atmosphere. Next workshop, when we talk about weather and climate. And later on, we're going to discuss the cryosphere, or frozen water in Earth's glaciers and ice sheets, in our geomorphology workshop, which is in a couple of workshops. So to understand water on Earth, we first have to understand water as a molecule. And all of you know the chemical formula for water, H2O. But if you look at water, the water molecule in a 3D sense, you'll notice that it has this bend to it. And there are sort of two things going on here. So firstly, oxygen is an atom that can accommodate up to 8 electrons in its outer shell, plus 2 in its inner shell, which are not shown here, which means that it can bond to, maybe not bond to 4 elements, but it has to have, for stability purposes, it has to have 4 pairs of electrons around it. Hydrogen, on the other hand, because its outermost valence shell is the first shell, it can only accommodate up to 2 electrons. So you can see with these bonds here, these covalent bonds, the oxygens and the hydrogens are actually sharing 2 pairs of electrons here. So the hydrogens are happy, but the oxygen needs 2 more pairs of electrons. So it has sort of sole possession of these 2 pairs of electrons here. And because these 2 pairs of electrons are they are negatively charged, they force the hydrogens into this bent shape here. Now, the other thing that's going on, other than the bent shape, is that oxygen has a higher electronegativity than the hydrogen. So it's actually going to pull all the electrons in the whole molecule a little bit closer on average to the oxygen than the hydrogen. So while the molecule as a whole is neutral, you'll notice that on a sort of statistical level, the sort of side with the oxygens and the pairs it has sole possession over will be slightly more negative, and the side with the hydrogens will be slightly more positive. And this has real world implications, most notably with hydrogen bonding. So this means that despite being a neutral molecule, the water molecules can bond to each other, and they can also bond to other stuff, making water an excellent solvent for dissolving things. Also, just for fun, I'll watch a video here, and you can see in this demonstration, what's happening is the person's turning on a faucet, and they bring in a sort of statically electrically charged comb, and you can see the water actually bends towards the comb due to that polarity. So the reason why we're spending so much time discussing this is that the polarity of water is really important for lending it several physical properties that have important implications for the Earth's environment. Firstly, because water bonds to itself so strongly, it has a very high what's called specific heat capacity. So you can put a lot of energy in it without it changing in temperature too much. And this is why our lakes and oceans, it takes a really long time for them to heat up. So they'll still be fairly cold in May or June when, during the northern hemisphere summer. But when you get to sort of July, August, and September, especially late August, early September hurricane season, they're still they're at their warmest, even though the days have already started getting quite a bit shorter by that point. Another interesting property is that water has a high surface tension, as you can see on this photograph here. So you can see this insect here actually walking on water because it's light enough and it has a high surface tension. As I mentioned earlier as well, water is considered the universal solvent, so it's very good at dissolving things into solution. We discussed this briefly in the last workshop when we talked about evaporite deposits, but it has many other implications as well for transporting different dissolved things like nutrients and salts and so on and so forth. Lastly, and this has a bit less to do with the polarity aspect, but water has a very interesting sort of density temperature relationship. So as many of you know, ice is less dense than liquid water, which means it floats. And this has to do with how the water molecules sort of arrange themselves in a solid form. But another interesting thing about water is it's actually densest at 4 degrees Celsius, and actually gets less dense as it goes down from 4 to 0. And it also gets less dense as it warms up. So its densest is not right before it freezes. There's this gap here. And this actually allows lakes to turn over sort of in the spring and the fall seasons, which allow sort of nutrients to recirculate throughout lakes in a lot of cases. And also because ice floats, it allows ice to form on top and insulate the rest of the lake, allowing, fish and other organisms to survive in the lake during the winter. So the fact that ice floats and doesn't sink to the bottom of the lake like it would for basically any other liquid on Earth is a really big deal for life. So that's just an overview of some properties of water. And in the next segment, we'll start talking about the water cycle.